Hello and welcome to another Lunch and Learn, AVL Lunch and Learn live on LinkedIn and on YouTube. Today I'm here with my colleagues Shan and Michael um, on an exciting battery topic. Shan is a CFD expert with more than 20 years of experience in the CFD simulation business, and Michael is a simulation expert with a focus on battery and optimization. And we will talk about thermal runaway in 3D simulation today. And with that, I hand it over to the two presenters today. And gentlemen, the floor is yours.
Yeah, for sure. Thank you, Thomas. Today's agenda, we're going to talk about regarding thermal runaway and 3D simulation. We're going to first talk about the customer pains and challenges. That's very, very important to sort of set the tone and the scope for why this is valuable. Then we're going to talk about the AVL approach to, assessing battery safety in respects to thermal safety. And then we're going to show some demo cases with some, real examples, customer examples, as well as internal examples. And then we're going to discuss the benefits and really wrap it up with that. So, we'll jump right into pretty much the customer pains and the challenges. So this is really where we're going to talk about product recalls, regulations, and some challenges through the development process.
And
So,
just before you jump in,
yeah, go
Michael,
ahead.
one more comment from my end. As this is live, you can comment on LinkedIn in the comments or on YouTube on the comments. I will have an eye on it and questions and forward them directly to the presenters. And yeah, with that, we really can jump into it.
Yeah, for sure. Appreciate that. Yeah, so definitely let us know if you have any questions. Write in, and we'll try to answer them as we go. Um, Pretty much some of the requirements and targets that people are having within the automotive industry regarding battery safety is they want to be able to have no more than I guess 5 minute for that's currently the legal requirement to make sure that the battery is safe for at least 5 minutes. Um, and then, there's other ones where you want it to actually be 15 to 30 minutes because it takes time for the fire department to show up. And in theory, you really don't want any propagation outside of the pack because, these vehicles will be parked in garages that can, cause peripheral damage to like the house or the parking structure where there's vehicles next to it. So in theory, just because you meet the regulation doesn't necessarily mean that that's the ideal product. The regulation is just there as a guidance, but we know that almost all the OEMs are wanting to have an ambition for no breaching of the pack. So, and this is an example of why you might want that. So this is a bus fire that had occurred in China. So you can see here that this bus was an electric bus. It caught fire, and there's other buses around it where this is actually spreading. So because you had the problem in one bus, it should be just contained to maybe the damage of that single bus, but because it breached the pack, you had it spread and cause other damage that otherwise it wouldn't have. And especially for something like this, when you have such a large amount of energy release and all these smoke and chemicals, you likely are going to have a evacuation of the vicinity because these are toxic gases. So the residents will also likely have to leave and quarantine from the area. So that's that shows pretty much the damage you can have on a thermal runaway there. This was another event that had occurred. There was, you guys may hear about these boats that catch fire while they're transporting, vehicles from, Europe to the U.S. or U.S. to Europe and Asia, wherever they go. But basically, this boat had 500 electric vehicles on board. And they mentioned during the emergency call that there was a fire that had started with the battery electric vehicle, and that effectively spread throughout the vessel and obviously caused the collateral damage of the other vehicles. But even more risky is fire at sea is like one of the worst things on a boat because there's not much you can do at that point, and it can definitely cause the boat to sink. So these are some of the challenges of why you want to have mitigation of that thermal runaway event. You either want it to be contained for as long as possible or if ideally never breach the pack. So these are just some of the thermal runaway consequences here. All of these are very loud events with these microphone here, but basically what you're seeing is you're seeing particle release here from when a thermal runaway event occurs. You're seeing venting into the vehicle underhood. So this is a breach, but it could be a strategic breach due to relieving pressure. So there's deformed packs that can occur during thermal runaway as well. And then you have melting and flammability. Obviously, here you could see the flame coming out of the pack and igniting the electrolyte. So yeah, that's pretty much those failure modes. And then what AVL really says is if you're trying to evaluate this under testing, it's very, very difficult to do that because you have so many different combinations and variations that can occur. So you have, thousands of cells in a pack, and you don't know which ones will actually go into thermal runaway. So you right there introduce a lot of variation and uncertainty. Um, Also, testing thermal runaway costs a lot of money. So just a single pack could be tens of thousands, if not hundreds of thousands, when you go to the prototype side of things. So these are quite expensive. Obviously, there's an environmental aspect, so you can only do this test in very specific places around the world. Is because due to what's released, so you need specialized facility. And finally, what AVL says is, ideally combine some of your testing initiatives as well as your simulation to better explore the design space. So you would use a test to obviously help parameterize your simulation. But then once your simulation, you have some confidence in it, you can do those studies, like I mentioned, where you're triggering different cells within the pack. You're also attempting to vary different pack designs so that you can see if you can actually contain the thermal runaway event. So these are just some of the pain points really that I'm going to summarize here, and then I'll pass it off to my colleague Shan. But yeah, so which concept is safer in terms of thermal runaway? You don't know that if you have no hardware that's available for testing. Is the battery operated under safety critical operating conditions? You obviously want to assess that, but it takes a very long time. You don't know if the pack is going to pass any of the certification tests because the experiments are dangerous and expensive. So you don't want to really iterate when it comes to certification. You want to be sure. And then, is your design what you're attempting to do here? Does it stop the thermal runaway or contain the thermal runaway? Usually, if it indicates that, that doesn't necessarily mean in the test that it will indicate that for all types of thermal runaway events. So the experiments don't really give a clear answer. And then, what if I change my cell chemistry or use old cells that are, repurposed or something? There's a lot going on about, second life batteries and things like that. Or what if I need to change cell chemistry to something better midway through the program or midway through the vehicle life? Can I still use the same pack design? This also is a challenge because you don't have many experiments to be able to run there. And like we mentioned, these are tens of thousands, if not hundreds of thousands per experiment. So effectively, this is the reason why AVL pitches this idea, and we have our customers doing it. We do it in our consulting projects where we do a blend of testing with simulation, because the simulation allows us to explore the design space and answer some of these questions. And so now I'm going to pass it off to my colleague Shan, where he's going to show you guys some really interesting simulations and show some cool stuff of what we do at AVL.
And you're muted. Just unmute yourself, please. Thanks.
Thank you. Thanks, Michael. Definitely, I can explain about our approach in addressing all the pain points that you show in the last slide and providing full thermal safety for any battery pack that customer has. Okay. And here the virtual battery development process is a key in solving all the battery thermal related problems. And here, first, I would like to address what are the modeling capabilities that we have and we use in this regard. During the normal battery operations, we know that the heat is being generated due to the continuous charging and discharging cycles. So accurate modeling of heat generation process is a first step. For that, we have 4 different methods where customers can choose it based on their inputs available and as well as based on their convenience. For example, we have a simple method called ohmic heating, and also we have equivalent circuit models where customer can give a discharge curves as an input for different C rates and different temperatures, so that they can get the parameters to mimic the actual heat generation process in the particular cell. And also, if you have a good amount of resources as well as good amount of time, then you can run a detailed electrochemical modeling to get the heat generation process as well. Let's say you don't have any of this and you don't have any idea about this particular cell and you don't have any material properties, anything about the cell, then we have a solution which is called ButTMO. The ButTMO has a cell library in-house, and they have mostly all of the battery cells available in the market, where customers can just go and choose the cell that they want to analyze, which directly gives the temperature distribution for the given operating condition. So once we get the correct temperature distribution, then we can include all the hazard scenarios, starting from basic thermal runaway basic effects. You can see there are a lot of basic effects, which I'll be going to the next slide, and including the advanced effects, including the solid body chemistry and particle ejections, arcing, and park deformations. So let's take a detailed look on what are the effects that in AVL we cover by using our AVL software, and what are the different hazard scenarios that we're able to simulate. So in this case, when I tell you about the basic effects, of course, the heat release is happening inside the cell because of the electrochemical reactions, and then once the heat is being released, the electrolyte starts to evaporate and pressure start to build inside the cell. And once the pressure reaches the certain level, where the vent opens in each cell, and then the venting gases are coming out. Once the venting gases are not coming out with just a gas alone. It has a harmful flammable gases, as well as it has particles, and it carries a high heat along with it. So wherever it goes, it starts to melt the components. And when it melts the components, makes the additional passage where the venting gases can easily flow through all of the places wherever it goes, it starts to heat the component, which is not really good for us, right? So that's happening all along the places. Once it transfers the heat along the way, and finally it finds the burst discs where the venting gases are really venting out from the battery pack. And along with it, we have a flammable gas. Of course, venting gases are not just, as I told you before, it's not only carrying the heat, it's also a flammable gas. It can, that's why we have seen in Michael's slide where the flames all over the places. So these are the basic effects that we have it. And here the video shows, I'm trying to run this video here. Okay, so technically what the video is supposed to show is, I'm sorry for the inconvenience here, the video is not running. So the video shows what are the components that we solve. Technically, we include all the battery pack components, including the housing, cooling passages, and E-boxes, and modules, and high voltage circuit pads. Everything is considered, okay? Everything is considered, and then once the thermal runaway happens on the battery level, but eventually it influences the whole battery pack itself, and also it goes into the vehicle, and it completely completely damages the complete vehicle itself. So understanding the underlying basic effects is a key, and heat release in the battery cell is caused by electrochemical reactions, and the heat release leads the vaporization of electrolyte, and pressure increases in the cell. Of course, as I mentioned before, after a certain time, it opens up the vent, and the rest of the basic effects takes care of it. Along with it, there are advanced effects also also in place. Arcing is possible, and solid body chemistry is possible, and particle ejection is possible, and pack deformation. Today, technically, I'm going to show.
Give me a section. The whole thing stopped for a sec here, so I apologize about that.
That's fine. You take a control and maybe you can drive it out. I don't mind.
Yeah. Give me 1 second. There's something that happened on PowerPoint here where we're presenting. So that's one of the curses of doing it live, but we try to do it for you guys. So if you guys doubted that it was live, now you
So
know.
yeah, in the meantime, this gives us time to answer actually a question that came
Yeah.
on LinkedIn. So the question was about how the chemical reaction for causing the fire is triggered. So if this is a chemical reaction or a short circuit. So maybe Shan, you want to comment on that? How do we trigger the thermal runaway in fire?
Yeah, technically the chemical reaction is because of the gases which is coming out through the venting, and venting gas is having the flammable gases. It has a hydrogen, it has a methane, and all several different components along with it, which is technically a multi-component fuel. If you consider the IC engine simulation, it's a multi-component fuel technically. And here, the hard particles which is coming out of the same cell, which acts as a ignition source. Of course, I'm going to talk about this next. So let me answer your question as well. Of course, remember AVL firearm was for internal combustion engines, and then we run the combustion all the time. So we use the same chemical reactions to solve the same physics here.
Okay, cool. Yeah, so it's back up, Shan. I guess you could
Thank
take
you.
it away. Yep. Hopefully this goes good.
Thank you. It's working really well now. Anyways, I already explained about this video, so
Yeah, so I guess this is what you're talking about with the heat release is caused by the chemistry reactions.
exactly.
In the
heat
cell.
release. Yeah, the heat release can be several reasons. That's also we are going to talk next. It can be a short circuit, or it can be a aging. It can be a degradation of the battery, or decomposition of the SEI, and all those things. And
yeah,
here,
so here's venting.
Yeah, venting is happening, and then melting is next. You can see melting happens around the places. And finally, here we see the venting gases going out of burst discs. Of course, that's not that's the last result that we wanted to simulate in our simulation environment, because our primary goal is to prevent the propagation itself. We don't want to have the gas goes all over the places and destroy everything and go out, because at that point it's really less advantage we have. Okay, now onwards we are going to discuss about the different hazard scenarios happening during the thermal runaway process. So first thing first, I'm going to talk about the arcing possibilities. Here the physical phenomena is whenever the short circuit happens on the battery module or a battery pack level during the thermal runaway, the breakdown voltage of air is decreased due to the venting gas and particles. So here, this is a physical phenomena, and in the bottom here we are showing that how we do it in a modeling, as well as what are inputs required. So technically, we use the physical approaches like Pascal law and measurements to develop an easy to understand arcing probability. And here the main inputs are, of course, the voltage and current involved in the battery modules, and the gas composition of the venting gas, and thermodynamic and mechanical properties of it. And here the animation shows the simulation results. Technically, we took 2 electrodes and then we put it in a certain distance, and then we ran the simulation by using the Pascal law, and then it calculates the breakdown voltage. And here you can see the results comparison between firearm and experimental data. And later we reduce the distance of it and to see what kind of breakdown voltage we get it. Technically, by reducing the distance, it reduces the breakdown voltage as well, which we clearly able to predict it. Now let's move on to the next topic, which is particle ejection during the thermal runaway process. Again, this one we slightly talked just a couple of slides before, where the thermal event happens. Inside the battery cells, the molten particles are exiting out from the battery cell, and then of course this is not only solid particles, this is also carrying the high heat. Wherever it goes, it melts the component, and here you can see in the simulation results the particle ejection is shown clearly, and as well as it deposits because of the gravity, as well as wherever it touches in the top, it melts the component. When it melts the component, the venting gas is happily traveling in the other directions because it got extra passage, and it can transfer the heat, and it continues to melt the other places. So this is also a very important thing to simulate, and here we are using the Lagrangian approach to simulate the particles with a combination of submodels for evaporation of electrolyte and deflection and fluid interaction between the venting gas to the solid. And here the main inputs are particle size and distribution, and material properties of the particles, and thermodynamic and mechanical properties of the venting gas. Moving on to the next one, which is solid battery chemistry. So in this case, the heat release within the battery cell is due to the decomposition of SEI and melting and reaction of the different components like cathode and anode, mainly driven by the chemistry, but it is possible that the chemical reactions happening with the cathode and anode materials also. So here how we simulate it? Here we simulate it by defining the anodes and cathodes as a representative species, and then we define their respective heat release and reaction mechanisms. So technically, here we use the detailed chemistry calculations of the battery components, and the battery components are defined as a representative species, and also we define the respective heat release and reaction mechanisms. The main inputs are mole fractions of representative species and reaction enthalpy for reaction equations of representative species, which is technically anode and cathode and different components into it. And then, as usual, we define the thermodynamic and mechanical properties of the venting gases. Here the video shows how we did it. And technically, the active components, the active materials contribute to the heat release mostly due to the electrochemical reactions. And then we can clearly see how the results looks like between the FIREM and the experimental results. The results are very well matching, and here the predictive modeling of heat release is also possible. Okay, coming into the last topic of the hazard scenarios. Here we all know that the venting when the thermal runaway happens, the venting gases are coming out. Of course, it comes out with high temperature as well as high pressure. Right. By that, the entire pack is swelling. The swelling is, you might have seen the several videos, how it first swells and then bursts. So swelling of the battery pack is quite common during this thermal runaway process. And also, if we don't include that in our simulation environment, then we might be missing very critical parameters. Like when the venting gases are going out, when we have the bulged geometries, it has more place to move now. So based on the new route, the temperature distribution of the next cells or next modules or the next components are going to vary. So it's very important in simulating the swelling effect in the simulation environment. For this case, we use a CFD and FEA workflow. Technically, from CFD, first, without any swelling, we run the simulation, and then we find out the temperature and pressure of the surfaces of the battery pack and the battery cell and other components, and then we give it to FEA, and they run the thermal deformation analysis, and they give the thermal deformation coordinates back to us, and then we morph the we implement the deformation in the FIREM mesh, and then we run the simulation. So this is how we can able to predict. You can see in the right hand side, you can predict on the there are two boxes here. One is undeformed mesh, another one is a deformed mesh. When the undeformed mesh, you can clearly see how the flow pattern, venting gas flow pattern is. On the other hand, when the swelling happened, when it bulged, you can clearly see how it looks like, right? And of course, we ran several validity cases. We ran a pouch cell. We ran a validity cases on the pouch cell, and we quantified the results comparing the propagation time between say, experimental and CFD, and also prismatic cell module. We ran the same simulation, and we varied the different installations, and then we validated the results as well. So along the way, our software is fully validated, and we have done so many customer projects as well. So here I'm going to show you some of the demo cases with the real examples. Okay, so here you can see this is 18650 module, and here the defective cell is 1, where the thermal runaway happens. In this case, this is a standard case, as well as we added installations around it and to see how the thermal runaway really propagates. This is all to get the 5 minutes the regulation rate. Here you can see without any installation, within 5 minutes, all the cells goes on a thermal runaway. On the right hand side, you can clearly see the defect cell goes on a thermal runaway, but even though it goes on a thermal runaway, because of insulation, we get 5.5 minutes of 5.5 minutes of time where the passengers can easily get out, because all of the cells are not going at a thermal runaway at all within 5 minutes. So when I see the battery study 2, here we varied the burst disk locations, BD1, BD2, and BD3. And here the color code shows which is safe, which is a borderline, which is not acceptable at all. In this case, you can see all are in the borderline, but the third one, the BD3, gives the better results where the temperature is lower, where it shows a lower possibility of thermal runaway. Okay, and of course, we ran several different analysis with the different strategies to prevent, delay the thermal propagation inside the battery pack. I just show you one of the case where it's a flame barrier. We introduced it in between the modules. Because of that, the venting gas, it really passes through on the sides, and it's not really melting the other components along with it. But on the other hand, it is really quicken the propagation inside the module itself. In the same module, it quickens the temperature distribution. It destroys the module itself. And here I give you back, Michael.
Appreciate it, Shan. Yeah. So yeah, those are pretty good use cases, and I think that encompasses a lot of capability within battery thermal runaway modeling that we have at AVL. This is a customer success story that we had with Vertical Aerospace. They're an electric airplane company, and they were wanting to understand thermal runaway of their battery packs, because when you're in the air, it's likely the last thing you want, just like when you're out on the open seas. And so we had a big project with them. We had a couple of like a timeline here that we've developed for them. And this is something we can do with any customer. And you can see here that we wanted to answer some questions, basically, is like, how does the venting affect the enclosure? What are some of the main thermal paths in case of a thermal runaway, and is the system safe? So we did a thermal propagation analysis on the module level, and we were analyzing venting, and we wanted to really target some heat transfer to the adjacent parts and understand that, as well as assess the enclosure temperatures and the outlet temperatures when it vents. So what we ended up doing was doing a thermal runaway study here, and we have more material here that we presented at our conference last year, that Vertical Aerospace, the work was presented there. And if you want to learn more, we can definitely have a discussion there. And this is effectively a thermal runaway of one of the cells within their module, and trying to understand the venting and what the temperature influence would be around the peripheral components there. And pretty much some of the benefits, just to summarize, if you guys had already seen it, is, which concept is safer. You can consider that through simulation. You can vary your concepts pretty quickly. Is the battery safe, operating under safety critical conditions? You can simulate those really off nominal cases. You can understand if your pack will pass certification before you actually spend the money to go do that, by testing and optimizing it virtually and then validating it, obviously, for the certification. You want to understand your countermeasures, so you can do that through simulation, where you're attempting to change the architecture of the pack. And then if you want to understand different cell chemistry or old cells on your thermal runaway capability of the pack, you can vary that within virtually and then redo the test. And I guess just to sum up one more thing, we have a question from Prakash. He's been quite engaged with us, which I appreciate. Is he wants to understand how can we make an aging analysis with the battery? He's really asking how many charge cycles can the battery sustain, and after that, what is its chance of thermal runaway? So we have a battery degradation model for battery performance and aging. It's electrochemical aging model. Where the chemistry will actually change within the battery as it's being cycled. Now, if you're trying to understand when exactly will the thermal runaway event occur based off of the changes in chemistry, that is a bit more complicated, and that's an ongoing area of research within AVL, as well as we're working with different OEMs on trying to answer that question, which is what I'd consider the golden question of battery safety effectively, is how often can I cycle my battery until it actually goes into thermal runaway, which is, quite a difficult thing to answer when you consider all the variations, manufacturing variation, chemistry variation, cell construction variation, things like that. So to say that was pretty much our presentation, and I guess I'll pass it off to Thomas to discuss what we got upcoming for our LinkedIn Live events.
Yeah, thanks for the great presentation, Michael and Shan. Just as a few housekeeping items, next week there will be no lunch and learn. We will support the Battery Workforce Challenge student competition as well as the Formula SAE competition. And in 2 weeks, we will continue with another battery topic, LFP graphite cells, how to operate that on a modeling study. And I think this is also very interesting with the regards to aging that was just mentioned. And with that, we like to conclude today's Lunch and Learn and hope to see you in 2 weeks again. Thank you and goodbye.
Thank you.
Thank you, everyone.